side, we're going to look at the definition, properties, and the operations of relations. First, let's learn about the definition of a relation. Binary relation. Let's say we have set A and set B. Then a binary relation R from A to B is a subset of A cross B. R is the ordered pairs where the first element is from A and second element is from B. A related to B or ARB denotes that element A, B is in this relation, while the notation below shows that A is not related to B. Now, let's move on to functions as relations. A function is a relation where each element of B is mapped to by only one element of A. Hence, we can see that a relation is a general of a function. Next is the relations on a set. A relation on a set A is a relation from A to A. For example, set A equals to 1, 2, 3, and 4. The relation such that A is less than B will be the 6 ordered pairs given below. Now, let's learn about the properties of relation. The first properties we're gonna learn today is reflexive. R is reflexive if for all element X in the set A, X is related to X. Now, let's look at the example of a set containing 1, 2, and 3. In this example, relation R is reflexive. It will be easier to understand this by drawing a directed graph and a 0, 1 matrices. A relation is reflexive if each vertices of the element in the set all have a loop. Relation also is reflexive if the highlighted diagonal of 0, 1 matrices all contain 1. The second property is irreflexive. A relation R is irreflexive if all element A in the set A, the ordered pairs AA, is not in R. In contrast with the reflexive relation, the directed graph here have no loop on each vertices. In addition, the highlighted diagonal of 0, 1 matrices all contain 0. Third property is symmetric. A relation R on a set A is symmetric if BA is an element of R whenever AB element of R. That is, a relation is symmetric if and only if A is related to B implies that B also related to A. Antisymmetric. A relation R on a set A is antisymmetric such that for all AB is the element of A, if AB is the element of R and BA is the element of R, then A equals to B. Now, we are going to look at the difference between symmetric and antisymmetric relation. In the symmetric relation, each link is bidirectional, which means that if we have AB, then we also must have BA, while in the antisymmetric, no link is bidirectional. Fifth relation is asymmetric, where for all A and B in set A, if A is related to B, then B is not related to A. We need to remember that every asymmetric relation is also an antisymmetric relation, but if it contains AA, then it is not an asymmetric relation. Now, let's look at the last relation, which is the transitive relation. A relation R on a set A is transitive whenever AB is the element of R and BC is the element of R, then AC is also element of R. For the transitive relation, when we draw the directed graph, if 1 is related to 2 and 2 is related to 3, then 1 is also related to 3. For the third part, we are going to learn about the operations of a relation. The first operation is the composite. Let R be a relation from set A to set B, where AB is the element in R. S is a relation from set B to set C, where BC is the element in S. The composite of R and S denoted by S composite R is AC. To help us understand it better, we're going to look at the example. Here we have set A, set B, and set C. They also have relation R from set A to set B and relation S from set B to set C. The composite of R and S is shown below. First, let's see relation R. 1 is mapped to 1. Then we find the ordered pairs in relation S which have 1 as its first element. In set S, 1 is mapped to 0. We can say that 1 from R is mapped to 0 in S. To get the answer, we repeat this process for all the ordered pairs in R. The second operation is the power relations. Let R power n, where n equals to 1, 2, and 3, be a relation on set A. To find R power of 2, we find the R composite R. To find R power of 3, we find R power of 2 composite R. Since we already know how to find the composite, then we can also find its power relation.
Part 2. Representations of relation. There are two ways to represent a relation: matrices and directed graph. First, matrices. We use 0, 1 matrices to represent a relation. Matrix element is denoted as 1 if it is an element of the relation. Otherwise, it is written as 0. In this example, the ordered pairs are written as 1 except 0, 3 and 1, 2 because they are not elements of relation. A matrix can be reflexive and symmetric. In the example, relation is reflexive. Therefore, there is a diagonal pattern of element 1 in the matrix. In this example, the original matrix is equal to its transpose. Therefore, the matrix is symmetric. Operations on matrices. First, union of two relations can be done using Boolean OR. Second, intersection of two relations can be done using Boolean AND. Product of two relations can be done by Boolean product. Power of relation. The matrix will multiply by itself according to the number of power. The second way of representation is directed graph. Digraph consists of a set of vertices and a set of edges. A relation is displayed from initial to terminal vertex. An edge with the same vertex is a loop. Two edges with the same vertices are parallel. This digraph is based on R. Edge 1, 1 will display a loop. Edges 3, 2 and 2, 3 are shown as parallel.
Part 3. Relational databases and equivalence relations. Usually we know that a relation of R between members of a set A is a set of ordered pairs of members of A. In other words, R is a subset of A cross A. For example, relation of less than that contain values of -1, 0, that means -1 is less than 0. So if you were given sets A1, A2 until AN, where A1, A2 till AN as domains and N as degree, the subset of A1 cross A2 cross until AN is an AND-array relation on these sets. A relation can be defined on any numbers of values, such as 2 for pairs or double, 3 for triple, quadruple, quintuple, sextuple, septuple, octuple, and so on. In all of these, we call it as n-tuples. A relation defined on groups of n values is called an array, and the groups within it are called n-tuples. While a database consists of n-tuples are called records,
at each of n tuples is called a field. Operations. Projection P maps the n tuple to the n tuple where n is less than or equal to n. For example, if we had a database of student records, then apply the projection P to 4 to the student records, we will get. Next operation is join, that combine two tables into one if they share some identical fields. For example, if we are given relation of y and r, so the join of y and r will be like this. A relation of a set is considered as equivalent relation if it is reflexive, symmetric, and transitive. And two elements related by an equivalence relation are called equivalent.